Hi everybody, my name is Noam Brown. This is joint work with my advisor Tomas Santom, and I want to talk to you today about our AI Libratus, which recently beat top humans in no limit poker. This is the first time that an AI has ever beaten top humans in this game, and we recently had a paper in Science that describes the details of the bot. I'm hoping that this talk will give a more high-level picture for people that are not as technically proficient in the poker AI research, and will give you some idea of the techniques that we've used in this bot. So to start with, obviously Libratus is designed to play poker, but the techniques that are used in the bot are not specific to poker. In fact, they are pretty general techniques that can be applied to any imperfect information game. Now these are not games like chess or Go, but rather, of course, games like poker, but more generally, any sort of strategic interaction that involves hidden information. For example, security interactions or negotiations. And I see this line of research as being particularly relevant to bringing AI into the real world, because most real-world strategic interactions involve some amount of hidden information. Now, when it comes to imperfect information games, poker has served as the primary challenge problem in game theory and AI, going back decades. In fact, if you look at the original papers on game theory published in the early 1950s, pretty much the only application that they discuss in the papers is poker. And the reason for this is that poker just beautifully captures the challenge of imperfect information. And in the past 12 years or so, there's been a lot of progress towards developing AIs that can play poker at higher and higher levels. One of the major breakthroughs was Rhode Island Hold'em being solved in 2005. Rhode Island Hold'em was a simplified version of Texas Hold'em, where there's only one whole card and two board cards. So it's like Texas Hold'em but smaller, which is why it was called Rhode Island Hold'em. And in 2015, Limit Texas Hold'em, Heads Up Limit Texas Hold'em, which is the smallest variant of poker ever to be played competitively by humans, was essentially solved by the University of Alberta. Now when it comes to poker, the variant that has been the primary benchmark and challenge problem for AI is a variant called Heads Up No Limit Texas Hold'em. This is a truly massive game. It has what's called a no-limit betting structure, which means that you can bet any amount you want between the minimum bet and the number of chips you have. So in our case, that's a branching factor of about 20,000. And the number of unique decision points, the size of the game, is about 10 to the 161. To put this in perspective, the number of atoms in the universe is about 10 to the 80. So we're talking about the number of atoms in the universe squared, and the size of Go is about 10 to the 170. No Limit Texas Hold'em is also by far the most popular variant of poker in the world right now. It's, for example, played on the World Series of Poker main event, and it's featured in popular movies about poker like Casino Royale and Rounders. And if you go to your local casino and you sit down and play some poker, I would say with greater than 90% probability, the table that you're going to be sitting at is going to be playing No Limit Texas Hold'em. Now the two-player variant allows us to determine objectively who is better, the AI or the human. When you have more than two players, there's a lot of issues that come up with collusion or kingmaker effects that might interfere with determining with certainty who's better, and I'll talk more about this at the end of the talk. And no prior AI has been able to beat top humans in no-limit poker. Now in the poker AI research community, there is an event called the Annual Computer Poker Competition, where all the different research labs and hobbyists that like to do research on imperfect information game AI get together and make an AI for a game like Heads Up No Limit Texas Hold'em, and play the AIs against each other to see which one is best. And in 2014, our AI, Tarkanian 7, won this competition. And in 2015, we upgraded the bot into a version called Cloudico that we played against 4 of the world's best heads-up no-limit Texas Hold'em specialists in the world. This was the first event between a top AI and top humans in this game. So we really didn't know what the outcome would be. And unfortunately, the AI lost to the humans by a margin of 9.1 big blinds per 100. Now, unless you're a pro poker player, this number 9.1 big blinds per 100 doesn't really mean much to you. But in the eyes of the poker community, it's considered a pretty sizable loss. The p-value was 0.08, so it wasn't quite statistically significant even after 80,000 hands of poker. But you could see by the way the bot was playing against the humans, it just wasn't at their level. Now, the 2015 competition taught us a lot about where the AI was weak and where it was strong. And we went back to the drawing board and redesigned a lot of the techniques that were used in the bot. And we came up with really innovative approaches to address some of the problems that we saw, which I'll get into more in the later parts of this talk. And in 2017, we produced a new bot called Libratus that we played again against 4 of the world's best heads-up no-limit Texas Hold'em specialists in the world. We played 120,000 hands over 20 days in January of 2017, and there was a $200,000 prize pool divided among the pros based on their performance to incentivize them to play their best. Here are some pictures from the competition. This is the first day setting up. This is what the user interface looks like for the humans. They were able to play 2 tables simultaneously if they wanted to. So while the AI was thinking on one table, they could play on the other. And the final result is that Libratus beat the top humans in this game by a lot, about 15 big blinds per 100. This was statistically significant at about 4 standard deviations, and each human lost individually to Libratus. And this game is a huge surprise to everybody involved. It was a huge surprise to the poker community, including the poker pros that we played against. It was a huge surprise to the AI community, and it was honestly even a huge surprise to us. In fact, if you had asked me at the start of the competition what I thought our odds were of winning, I would have put our odds at maybe 2 to 1 in our favor. But I thought it was going to be very close, and I was very concerned that given the number of hands that we were playing, we would not be able to reach statistical significance. And I was also very concerned that the humans would find some weakness in the AI, and they would just be able to steamroll the bot for the rest of the competition. So basically, I thought either we would squeak out a small win, or the humans would just absolutely wreck the bot. I thought the odds of winning by a margin like 15 big blinds per 100 was basically 0. And I think the poker community was even more pessimistic about the bot's chances. When we first announced the competition, there emerged a very active betting market on the outcome of the competition. Because they're poker players, obviously it was a very popular thing to bet on. At the start of the competition, the betting odds against us were about 4 to 1. And I think it wasn't until about 3 days into the competition, after we had won for 3 straight days, that the betting markets finally were in our favor and people were saying that, oh, hey, maybe this bot actually has a chance of winning this thing. And I think it wasn't until about the 7th or 8th day that you could no longer bet on the outcome of the competition. You could only bet on how much the humans would lose on each individual day. Now, one question I often get is, well, why are imperfect information games like poker so hard in the first place? After all, we have Deep Blue that can play chess at a superhuman level. We have AlphaGo that can play Go at a superhuman level. And in fact, you might have heard recently about this new algorithm called AlphaZero that came out of DeepMind, which can play Go, chess, and shogi all at a superhuman level using the exact same algorithm. So why can't we take something like AlphaZero and just plug in a game like poker, and why won't it perform at a superhuman level? And there's a few reasons for this, but the main one is that in an imperfect information game like poker, it's no longer possible to determine the optimal strategy for a subgame using information about that subgame alone. Let me show you what I mean. In a perfect information game, you take some action, your opponent takes some action, and you find yourself in a particular subgame, and now you can forget about everything that came before it. All of that information is now irrelevant. The only thing that's relevant for determining the optimal strategy from this point forward is the particular subgame that you are now in. And this is really useful because now if you're playing a game of chess, for example, and I were to show you this chessboard, and I told you it's white's move to act, what should you do? You don't have to know anything about the strategy of chess. You don't have to know about the Sicilian defense or the Queen's Gambit. You don't even have to know how we got to this particular situation. All you have to do is a search over the possible different moves you can make, and you can see if you move your white queen to that square, then according to the rules of chess, it's checkmate, game over. So obviously that's what you should do. And in imperfect information games, you actually can't do this. In imperfect information games, you take some action, your opponent takes some action, and you find yourself in a particular subgame. But now, some other subgame that you did not reach, and in fact you cannot even reach from this point on, can affect what the optimal strategy is for the subgame that you are in. This is kind of a counterintuitive idea to a lot of people. It's not at all obvious when you first see it, but I'm going to give you a concrete example of this later on in a few slides that will demonstrate this. But before we get to that, I want to talk a little bit about what we're actually trying to do in these games. Our goal is to find what's called the Nash Equilibrium. This is a profile of strategies, one strategy for each player, where if the players are playing these strategies, they cannot improve by deviating to a different strategy. You can basically think of it as the optimal strategy for the game. In two-player zero-sum games in particular, which is what this paper focuses on, playing a Nash Equilibrium guarantees that you will not lose an expectation. That is, no matter what your opponent does, the worst that you can do is tie an expectation. And in practice, you're probably going to win, especially in a complicated game like poker where your opponent might make mistakes. And a Nash Equilibrium is actually guaranteed to exist in any finite game. And this is kind of a surprising result to a lot of people, that there exists a perfect strategy for a game like poker. But in fact, it's not too surprising if you think about it. Think of an example like rock, paper, scissors. Everybody knows what the optimal strategy is in a game like rock, paper, scissors. You just randomly throw 1/3 probability for rock, paper, and scissors, and now no matter what your opponent does, you're guaranteed to not lose an expectation. The same sort of solution exists in a game like poker, but obviously it's way more complicated, and we have no hope of finding it exactly, especially in a complicated game like Heads Up No Limit Texas Hold'em. But we can approximate it using different techniques that I'll introduce in a little bit. And in a complicated game like poker, and obviously in a game like rock, paper, scissors, yeah, you're guaranteed to not lose an expectation, but also you're not going to win an expectation if you just randomly pick between rock, paper, and scissors with 1/3 probability. But in a game like poker, which is very complicated, if you're playing the Nash Equilibrium, you're probably also going to win in practice because your opponent is going to end up making mistakes, and you're hopefully not. So that's our goal. It's to find the Nash Equilibrium for this game, and we're going to measure our performance. In addition to performance against top bots and top humans, we're also going to measure something called exploitability. This is distance from a Nash Equilibrium. It's how we would fare against a worst case adversary. Now you might ask, well, why should we care about exploitability at all? Well, certainly it's important to be able to beat top humans, but it's also important to be robust to your opponent adapting against you. And I think 2 recent man-machine matches have really highlighted the importance of this. One is the recent OpenAI match in Dota 2, and the other is AlphaGo against Fan Hui. If you look at the OpenAI match, they managed to beat top humans in 1 versus 1 Dota 2 in just a few games, about 3 games I think against the top player. And then after that, they opened it up to the general public and invited them to play thousands of matches against the AI to see if they could find any weaknesses that they could take advantage of. And in fact, pretty mediocre players managed to find certain key weaknesses in the Dota 2 bot that allowed them to beat it pretty consistently. And this isn't just with OpenAI and Dota 2. In fact, if you look at the original AlphaGo, the one that beat Fan Hui, it beat him 5-0, but then they invited Fan Hui to play several more matches against it and to see if he could find any weaknesses in the AI. And in fact, he found certain situations, what they call delusions, where the AI would consistently underperform, and he could take advantage of it. And obviously they had to fix this before the Lee Sedol match. And so I think what this highlights is that it's not enough to beat top humans once or twice or 5 times. You have to be able to be robust to the opponent adapting to you. This is particularly important if you want to deploy this on a large scale in the real world. But in our AI, Libratus, we played against the top humans for 20 days, 120,000 hands of poker. And that whole time, the 4 humans were working as a team to try to take advantage of the AI in any weakness they could find. And in fact, they actually coordinated how they would explore and exploit the bot to try to find these weaknesses. But ultimately, they were not able to find weaknesses that they could take advantage of. And I think one of the key reasons for this is that we cared about exploitability. We wanted to find a strategy that was not going to beat them just once or twice, but was going to be robust to them adapting against it. So keep that in mind as we go forward with the talk. Now I'm going to introduce a simple imperfect information game that I call coin toss, and it's going to be used as an example of why imperfect information games are so difficult. In this game, player 1 starts by flipping a coin that lands heads or tails with 50-50 probability. Player 1 is going to observe the outcome of this coin toss, and player 2 is not. Now after the coin lands, player 1 has a choice. They can either choose sell or they can choose play. If they choose sell, then the game is going to lead to a separate subgame, the details of which are not important, but the expected value of which is important. We'll say if the coin landed heads, then it was lucky, and player 1 can get an expected value of 0.5, 50 cents, by choosing sell. On the other hand, if the coin landed tails, then we'll say it was unlucky, and by choosing sell, player 1 gets an expected value of minus 0.5. On the other hand, player 1 can choose play, and if they choose play, then the action goes to player 2, and now player 2 has to try to guess the outcome of the coin toss, but keeping in mind they did not observe how the coin actually landed. If they guess correctly, that is, they guess heads and the coin actually landed heads, then player 1 is going to lose $1, and player 2 is going to gain $1. Here the payoffs are shown only for player 1. Since this is a 2-player zero-sum game, player 2 is just going to receive the opposite of whatever player 1 receives. On the other hand, if player 2 guesses incorrectly, that is, they guess tails and the coin actually landed heads, then player 1 is going to gain $1, and player 2 is going to lose $1. And you can see there's a dotted line between the two player 2 nodes. This means that they're in what's called an information set. Since player 2 did not observe how the coin landed, player 2 doesn't know which of those two nodes they're actually in when they observe player 1 choose play. And so their strategy has to be identical for both of those nodes. Now I want you to imagine that you're player 2 in this game, and you just observe player 1 choose the play action, so you know you're in this imperfect information subgame that's shown. What should you do? Should you guess heads or should you guess tails? Well, one option is to just always guess heads. But obviously this is a really bad idea because now player 1 is going to get an expected value of 50 cents when the coin lands heads by choosing sell, and an expected value of $1 by choosing play when the coin lands tails. So on average, they're going to be getting 75 cents in this game. Another strategy is to always guess tails, but this is also a really bad idea because now player 1 can get an expected value of $1 by choosing play when the coin lands heads, and get minus 50 cents by choosing sell when the coin lands tails. And sure, they're getting an expected value of minus 0.5 when the coin lands tails, but that's better than choosing play and getting an expected value of minus 1. So on average, player 1 is getting 25 cents in this game if we always choose tails. So what should we do? Well, it turns out that the optimal strategy in this game is to mix. You should guess heads with 25% probability and tails with 75% probability. And if you do this, then player 1 gets the same expected value for choosing play that they would for choosing sell. And when the coin lands heads, they get 50 cents, and when the coin lands tails, they lose 50 cents. So on average, they're getting an expected value of 0. But now let's say we change this game a little bit. Let's say instead of the coin being lucky when it lands heads, it's actually lucky when it lands tails. So we're going to swap the payoffs for the sell action. We'll say that when the coin lands heads, the expected value for choosing sell is now minus 0.5. And when the coin lands tails, the expected value for choosing sell is now 0.5. Well, it's pretty clear in that case that our strategy as player 2 should change as well. Now we should be guessing heads with 75% probability and tails with 25% probability. But you can see what's happened here is that by changing the expected value of the sell action, we have affected what the optimal strategy is for player 2 in the play subgame. And this is something that can't happen in perfect information games. Perfect information games are a special case where you don't have to worry about this, and you could find the optimal strategy in a subgame using only information in that subgame alone. In imperfect information games, which are a more general case, when you were trying to find the optimal strategy in any particular subgame, it might depend on what the strategy is in other parts of the game tree that are completely unrelated. Here, the sell action is not part of the subgame, the play subgame, and in fact it's not even on the path leading to the play subgame. So this is the major challenge of imperfect information games. That said, there is some hope. You can see here that there is a whole, I mentioned before, there's a whole subgame that follows the sell action. But the details of that subgame are not actually important to determining the optimal strategy in the play subgame. The only thing that's relevant is the expected value that player 1 could have received by choosing the sell action instead, not their strategy that follows that action. So what we can do in Libratus is we don't try to determine the optimal strategy in the sell subgame if we're trying to find the optimal strategy in the play subgame. Instead, we're just going to try to estimate what the expected value is that player 1 could have received by choosing the sell action. And this leads to Libratus. In Libratus, we have this massive game, Heads Up, No Limit, Texas Hold'em, that's simply way too large to solve up front. So instead what we're going to do is come up with a really good approximation of the optimal strategy just for the early part of the game. And now for the later parts of the game, we're just going to try to approximate how to play. Give us a rough sketch. And now during actual play, when we find ourselves in a particular subgame, we're going to come up with a much better strategy for that particular subgame, while fitting it within the overarching blueprint strategy that we've already computed. That is, we're going to use information about the expected values of those other subgames in order to determine the optimal strategy in the subgame that we find ourselves in. And now we're going to repeat this process as we go down the game tree. When we find ourselves in another subgame, we're again going to come up with a much better strategy for that particular subgame while fitting that solution within the overarching blueprint that we have computed so far. So you can see that there are three main modules of Libratus. The first module is called Abstraction and Equilibrium Finding. Here, the AI is just trying to find a rough approximation for how to play in the entire game as a whole. This is done entirely offline before the competition ever began, and it accomplished this using the algorithm called Counterfactual Regret Minimization, which is a self-play algorithm that I'll get into a little bit later. The second module is called Subgame Solving. Here, when the AI is actually playing in the competition against humans, it will look at what situation it's finding itself in, and will come up with a much better strategy for that particular situation. But again, fitting it within the blueprint it's already computed. The third component is called the self-improver. Here, the AI reviews the hands that have occurred in the previous day, and it looks at what situations its opponents have put itself in that the AI might not have a very accurate blueprint strategy for. And it tries to come up with a much better blueprint strategy in those particular situations, so it's more robust to those kinds of attacks the next day. So in this way, the AI is constantly improving its blueprint strategy and getting closer and closer to equilibrium play. Now I'm going to review each of these modules one by one, and I'll start with the abstraction and equilibrium finding component. So I mentioned before that imperfect information games have this challenge where you cannot determine the optimal strategy for a part of the game in isolation. And this is a very difficult challenge to overcome. Perfect information game AIs like Deep Blue and AlphaGo have put a lot of emphasis on real-time computation, finding the optimal strategy for the given situation that they're in. And actually, if you look historically at how AIs have approached imperfect information games, they've taken a very different approach. Instead of doing a lot of online computation, they actually have done pretty much all of their computation offline before play ever begins. They try to come up with a single strategy for the entire game as a whole, and then when they're actually playing, they'll just look up what situation they're in and see what the pre-computed strategy is for that particular situation. And this has had a lot of success, actually. If you look at the early versions of poker, for example, Rhode Island Hold'em, which has 10 to the 9th decision points, that was solved by first compressing the game down to a smaller size using a lossless compression algorithm, and then solving the entire thing up front using a linear program. So that every decision point had a pre-computed solution. And even Limit Texas Hold'em, which has 10 to the 13th decision points, that game was essentially solved by first compressing the size of the game down to a smaller size so that it could fit on a supercomputer, and then running an iterative convergence algorithm that slowly converged to a Nash equilibrium over time. And again, in both of these cases, the strategy was entirely pre-computed. There was no actual online computation occurring in real time. But No Limit Texas Hold'em is simply way too big. At 10 to the 161 decision points, it's completely impossible to pre-compute a strategy for every decision you might be in. And in fact, it's also impossible to even traverse the entire game tree just once. So what we do for a game of this size is something called abstraction. And this has been around for a while. The idea of abstraction is that you have this game that's simply way too big, 10 to the 161 decision points. And we're going to try to compress that game down to a smaller size while retaining as much as possible the strategic characteristics of that game. And then we're going to solve this smaller version of the game and use its solution when we're playing in the larger game. So when we find ourselves in a particular situation in the larger game, we're going to map that state to a state in the smaller game and look up what the solution, the optimal strategy is for that particular situation in the smaller game. And hopefully that gives us a good approximation of how to play in the original larger game. Now there are two main kinds of abstraction. The first one is called action abstraction. Here the idea is that you might have a very large branching factor in the game. For example, in a game like No Limit Texas Hold'em, you have a branching factor of about 20,000 because you can bet any dollar increment up to $20,000. But there really isn't that much of a difference between betting $500 and $501. You can make a very good poker AI that only considers bet increments of $100, for example. So you can reduce the complexity of the game considerably by creating an abstraction that only has a smaller number of bet sizes. And that actually works surprisingly well. You can make a very strong AI that only has a few different bet sizes in poker. But you run into a problem. You can certainly limit yourself to only betting increments of $100, let's say. But what happens if your opponent bets something like $510 and you only have $500 and $600 in your abstraction? Well, one thing to do is simply round it to a nearby size and say, okay, well, $510 really isn't that much different than a bet of $500. So I'll just treat it as if it were a bet of $500 and respond accordingly. And that's called action translation. And the technique works fairly well, but we are going to introduce a new technique later on that is going to do much better. And actually, action translation was one of the main weaknesses of Cloudico, because the humans were able to use unusual bet sizes that confused the AI and caused a lot of rounding error. Another form of abstraction is called card abstraction, more generally information abstraction. And here the idea is that there are billions of different possible poker hands in a game like poker, but there might not be huge differences between a lot of them. And so you can reduce the complexity of the game by quite a bit by grouping certain hands together and bucketing them and treating them identically. So for example, instead of having to come up with a different strategy for a king high flush or a queen high flush, you could treat them identically and only have to come up with a single strategy for both of those hands. And this works pretty well, but when you're playing against top humans, some of these subtle differences between the hands that are bucketed together could be the difference between winning and losing. For example, if you look at these two hands, 5 of diamonds, ace of clubs, and 5 of diamonds, ace of spades, on this 5-card board, they pretty much beat all of the same hands, and they pretty much lose to all of the same hands. but you might actually want to play them fairly differently. And the reason is that the best possible hand that your opponent can hold is the ace of spades plus another spade, which gives them an ace-high flush. And if you are holding the ace of spades, like you are in that bottom hand, then you know that your opponent can't have an ace-high flush. So you can bluff much more effectively because your opponent would only call you if they had a good hand. And if they don't have the ace of spades, you know they can't have an ace-high flush, and so they're less likely to have a really good hand that they could call you with. So with the 5 of diamonds, ace of spades, that's a really good hand to bluff with. And with the 5 of diamonds, ace of clubs, you probably just want to check and play it safe. So even though these hands pretty much beat all the same hands and pretty much lose to all the same hands, you actually want to play them very differently. And I think that this is one of the major weaknesses of Cloudico. It grouped these hands together, and then it would get very confused. It would sometimes try to bluff when it had the 5 of diamonds, ace of clubs, or it might try to check when it has the 5 of diamonds, ace of spades. It wouldn't understand what's called these blockers very effectively. And we improve this in Libratus. Even though we do card abstraction to calculate the expected values for subgames, when we're actually computing those improved strategies in those subgames, we don't use any card abstraction when actually playing. So in Libratus, we actually use no card abstraction at all on the first 2 betting rounds. And the action abstraction is very dense on those rounds as well. There's maybe about 10 different bet sizes, both for ourselves and for the opponent. And this is important because on those 2 betting rounds, we're actually just playing according to the pre-computed strategy. We're not doing any real-time computation at all. When it gets to the 3rd and the 4th betting round, we use a lot of card abstraction and a fairly sparse action abstraction. Only 2 or 3 different bet sizes, depending on the situation. And this is helpful because the 3rd and the 4th betting rounds are exponentially larger than the 1st and the 2nd betting rounds, because the game tree blows up exponentially in size as you go farther down the game tree. So this means that the total size of the abstraction is about 50 terabytes, which isn't too bad if you have a supercomputer. Now, we are using card abstraction on the 3rd and the 4th betting rounds, but that's only for the blueprint strategy, the strategy that's pre-computed before actual play begins. So we're just using this information to calculate the expected values on the 3rd and the 4th betting round. During actual play, when we get to the 3rd betting round, we're not going to play according to the pre-computed blueprint strategy anymore. We're instead going to apply subgame solving and come up with a much better strategy in real time that has no card abstraction and a very dense action abstraction on those 2 betting rounds. So the abstraction on the 3rd and the 4th betting round are only being used to approximate the expected values for these different subgames. Now, once we've constructed the abstraction for the game, we're going to compute what's called the blueprint strategy. This is the pre-computed solution to this simplified abstract game, and we're going to improve upon that in real time when we're actually playing. And we compute the blueprint strategy using an algorithm called Monte Carlo Counterfactual Regret Minimization, plus some additional twists that I'll get to in a little bit. MCCFR is an iterative algorithm, and it's fairly similar to reinforcement learning self-play, but a little bit different. The idea is that on each iteration, one player is going to traverse the game tree and update their regrets, and the other player is going to just sample actions. Regrets roughly correspond to how much a player regrets having not taken an action in previous iterations, and there is a single regret value for each action that a player can take at every decision point. So let's say, for example, player 1 is traversing the game tree, and player 2 is just sampling actions. And the player that traverses the game tree switches back and forth on each iteration. So player 1 starts by picking an action in proportion to the amount of regret that they have on those actions. Here, because the regrets start at 0, player 1 just picks an action at random. And then we might encounter a player 2 node, in which case player 2 is going to sample an action according to their regrets. Now, since the regrets are all 0, again, they just randomly sample an action in this case, and they're going to update their strategy sum, which is a tracker of the average strategy they've played over all the iterations, and increment the action that they chose by 1. When we encounter another player 1 node, we again choose an action in proportion to the regrets and explore that action. And eventually we receive some terminal reward. For example, let's say $50. And now player 1 is going to investigate each of the other actions that they could have taken, and find out, hypothetically, what reward they would have received for these other actions. For example, they might say, okay, well, if I had chosen this middle action instead, I could have gotten a hypothetical reward of $0. Or if I chose the right action, I could have gotten a reward of $100. And they update their regrets accordingly. so that now the regrets are updated as the difference between what they could have gotten for some action versus what they actually got. For example, that right action, they could have gotten an expected value of $100, and they actually got a reward of $50. So they will increase the regret on that right action by 50. And this is actually very similar to how humans learn to play poker. If you've ever played poker, you know it's very common for a person to ask, well, hypothetically, if I were to bet, would you have called me? And that's exactly what we're doing in MCCFR. We're investigating hypothetical other actions and finding out what the reward would have been for those other actions. And since we're just playing against a copy of ourselves, we can query and ask, would you have called me if I had bet there? And the bot will be able to answer that question. Now, after updating the regrets at the bottom decision node, we're going to pass that reward up that we actually received, the reward of $50. And we're going to repeat the process at every decision node that we encountered along this in this iteration. So we're again going to explore the other hypothetical actions we could have taken and find out what the hypothetical reward would have been for those other actions. So for example, for this right action, we're going to explore it, and if we again encounter another player 1 node, we're going to sample an action in proportion to the amount of positive regret on those actions. So in this case, since the regrets are 0, that means picking an action uniformly at random. Let's say we pick the left action and we get a reward of minus $500. We'll then explore the other actions, and maybe we receive a reward of $100 for the right action. So then we're going to update the regrets accordingly. And then we pass up the reward that we actually received, which in this case is a reward of minus $500. And that becomes the hypothetical reward for having chosen the right action at the root node. We're then going to update the regrets at the root node, and then that completes the first iteration of MCCFR. On the second iteration, we traverse the game tree for player 2, exploring all of the player 2 actions that we encounter, while only sampling with a single action at player 1 nodes. And then again, we go back to traversing the game tree for player 1, and in that case, we'll explore all the actions for player 1, and we will pick actions that have positive regret with higher probability. Now, Libratus uses an improvement to MCCFR called regret-based pruning. The idea here is that there are a lot of actions in a game like poker that are just clearly bad, that have very negative expected value. For example, at the beginning of the game, you always want to fold 2-7 offsuit. Raising with 2-7 offsuit, which is the worst hand in poker, is a very negative expected value action. And you also don't want to fold the best hand, for example. And these are things that humans pick up very quickly. But MCCFR, even if an action has consistently been giving very negative rewards, it will still explore those actions on every single iteration. So for example, that right action, even though it's given you a hypothetical reward of minus $500, you'll still explore it on the next player 1 iteration to see, well, what is the hypothetical reward this time around? And intuitively, if an action is consistently giving you very negative rewards, then you can spend less time exploring it. You should realize eventually that, hey, this action is a pretty bad action. I'm wasting time constantly trying to explore this iteration. I'll be better off spending my time and resources on parts of the game tree that are actually useful and that I'll actually encounter in real play. And that's the idea of regret-based pruning. The idea is that if an action has very negative regret, we can actually skip it. We don't have to traverse it every single iteration. And in the unsampled case, this actually has theoretical guarantees that says it will not hurt performance in terms of number of iterations. You'll still converge to a Nash Equilibrium just as quickly. But you will conduct every single iteration much faster because you have to explore less of the game tree on each iteration. And in practice, it can give you an order of magnitude or 2 improvement in performance. In the sampled case, there's not theoretical guarantees currently, but empirically, it also seems to give very good performance. And in the case of Libratus, it allowed us to solve abstractions that were about 4 times larger than were otherwise possible. So after running MCCFR on the abstraction, we take the average strategy over all the iterations that we've done, and that gives us the blueprint strategy, the solution to the abstraction. And we're going to move on to the second component where we try to improve that abstraction in real time using subgame solving. So once again, subgame solving is this idea that when we encounter a part of the game in real time, a subgame, we're going to improve upon it while fitting the solution within the overarching blueprint we have so far. Now, when I talk to people about subgame solving, the first idea that people always suggest is, well, we have this blueprint strategy, we have this estimate of how we expect both players to play in the game. It might not be perfect, but why don't we assume that the opponent is going to play according to this blueprint, and then when we encounter a subgame, we're going to come up with a better strategy in real time that responds to the opponent playing that way. And in particular, we can update our beliefs about what state we're in, and then when we reach a subgame, we solve it assuming that that belief is correct. This is called unsafe subgame solving. Let me walk you through an example of this in the coin toss game. So the idea here is that when the coin first lands, we know that we're in one of these states with 50-50 probability. And this is true. This is objectively true. And now we have this blueprint strategy of how we expect player 1 to play. We might say that, well, according to the blueprint, we expect them to choose play with 80% probability if the coin landed heads, and 30% probability if the coin landed tails. So if we observe player 1 choosing play, then we're just going to update our belief about what state we're in, and we're going to say, okay, well, since they usually chose play when they're in heads, and they chose it less often when they're in tails, we'll now say that there's a 73% probability that we're in the left node, and 27% probability that we're in the right node. And you arrive at these probabilities simply by applying Bayes' rule. And now the idea is that, well, we're just going to assume that these probabilities are correct, and then we will compute a player 2 strategy that best responds to this probability distribution. But in that case, that would mean choosing heads with 100% probability, which we've already established is a very bad idea, because now player 1 can simply change their strategy and adapt to us, and always choose sell when the coin lands heads, and always choose play when the coin lands tails. So this idea of maintaining a belief distribution about what state you're in, and then when you encounter a subgame, finding a best response to that belief distribution, this approach is not a good one. And the reason is because you're making a very strong assumption about how the opponent is playing. You're assuming that they're playing according to this blueprint strategy, when in fact they have no reason to do so. The blueprint strategy gives one equilibrium, or one approximate equilibrium, but it's not the only one, and there are a lot of strategies that the opponent can use if they assume that if we are in fact playing according to that equilibrium. So unsafe subgame solving, in theory and in many cases in practice, can lead to very high exploitability. It will make us very vulnerable to opponent adaptation. That said, empirically in poker, it does often work in some cases. And so it's not necessarily a bad approach to use in certain situations, particularly in large games. But there are no theoretical guarantees, and you can construct cases like this one, for example, where it can lead to very, very poor performance. Another example of why unsafe subgame solving is a really bad idea is what happens if the opponent chooses a nonsensical action, an action that we think should occur with 0 probability. For example, let me give you a concrete poker example. Let's say you're playing poker against somebody for the very first time. You've never played a hand of poker against this person before. You sit down at the table for the very first time, and the very action that they do is shove all in for all of their money. What should you do? Well, this is what a lot of poker players would say, okay, well, you should try to estimate what their range is, what cards they would do this with. The problem is that this action should be taken with 0 probability with all of their hands, so their range is undefined. So do you assume that they have the best possible hand, pocket aces? Do you assume that they have a uniform random distribution over their hands? Both of those are really bad ideas. So what we use on Libratus instead is a technique called safe subgame solving. This is a technique that was first introduced in 2014 and has been improved upon since then. And our latest, the latest version of this technique that was introduced in our NIPS 2017 best paper makes it, for the first time, far more effective than unsafe subgame solving. And the idea here is that we're not going to make any assumption about how the opponent is playing. We're not going to make any assumption about their strategy. Instead, we're going to make an assumption about the values that they could receive in an equilibrium by playing against our equilibrium strategy. And then we're going to try to find a strategy in real time that makes them worse off for having chosen this action, this shove all in action, than what they could have alternatively gotten for choosing some action in the equilibrium. So for example, it could be the case that for 2-7 offsuit, the thing that they should have done in an equilibrium is choose fold, and that would have gotten them an expected value of minus $50. And with 4-8 offsuit, their best bet would have been to choose call and get an expected value of $25. And with pocket aces, maybe the best thing that they could do in an equilibrium is raise a small amount and get an expected value of $1,000. And now, in real time, we're going to try to compute a strategy that makes them worse off for choosing this action that we actually observed, the shove all in action, than what they could have alternatively gotten for having chosen an action that was part of a Nash equilibrium. And of course, if we can do this, if we can ensure that they are actually worse off for having chosen this action than what they could have alternatively gotten in a Nash equilibrium, then we are guaranteeing that they are getting a lower expected value than what they would have gotten in a Nash equilibrium, and therefore we're going to end up winning an expectation in the long run. Now, this might not always be possible. It might not always be possible to make them worse off, but at the very least, we should be able to make them no better off than some action that they could have taken that's part of a Nash equilibrium. Now, we're making a strong assumption here. The strong assumption is that we know the expected value that they could have gotten in a Nash equilibrium. We're assuming that we know that with pocket aces, they should have received an expected value of $1,000 in a Nash equilibrium. And we don't know that for sure because we don't have a Nash equilibrium solution. We don't know what the Nash equilibrium values are. That said, we can use the blueprint strategy to estimate these values. And we have a theorem that says as long as these estimated values are close to the true values in a Nash equilibrium, that is, if the blueprint strategy is giving us accurate estimates of the Nash equilibrium values for actions, then subgame solving, safe subgame solving, is going to produce a strategy that is close to a Nash equilibrium. So then the question is just how good are our estimates? How good are the blueprint estimates of the Nash equilibrium values? And it turns out that using this abstraction technique gives us surprisingly good estimates of what the values of actions are in a Nash equilibrium. As a test of this, we constructed this game called Flop Texas Hold'em. This is a simplified version of No Limit Texas Hold'em, where there are only 2 betting rounds instead of 4. And we constructed an abstraction of this game that is just 0.02% of the size of the full game. And we solved this abstract game, and we looked at the strategy that it produced. And it turns out that the strategy it produced was pretty poor. If player 1 played perfectly against player 2, player 2's abstract strategy solution to this game, then player 1 would have won by a rate of 112 millibig blinds per hand. This is another win rate in poker. And if player 2 played perfectly against player 1's strategy in this game, then player 2 would have received an expected value of 21 millibig blinds per hand against player 1's solution to the abstract strategy of this game. Nevertheless, the estimated expected value to player 1 in the abstract game was 35 millibig blinds per hand. So this is what the abstract solution estimates player 1 should receive if both players are playing perfectly. And the true value was actually 38 millibig blinds per hand, so fairly close. So what's going on here is that even though abstraction is giving us a pretty bad strategy, it's giving us a good estimate of what the players should receive for these in the game. And you can think of this as somewhat analogous to random rollouts in Monte Carlo tree search. In Monte Carlo tree search, you reach some depth limit. One thing you could do to get an estimate of the value of those leaf nodes is do random rollouts. And obviously, playing according to a random policy beyond some depth limit is a really bad idea. That's a really bad policy. But it gives fairly accurate estimates of what those values what the value is for those leaf nodes. And abstraction is doing something similar. It's giving us very bad policies, but it's giving us very accurate estimates of the values of those actions. Safe subgame solving also allows us to get around one of the other major challenges of a game like No Limit Texas Hold'em, which is the extremely large action space. I mentioned before that No Limit Texas Hold'em has a branching factor of about 20,000. And when you're dealing with a game that has a branching factor that large, one thing you can do is a technique called action abstraction, where you only consider a small number of those actions. For example, maybe only bet increments of $100 instead of all 20,000 actions. And this works fairly well. But let's say you have $500 and $600 in your abstraction, and your opponent bets $550. Well, what do you do then? In the past, you'd have to round it to a nearby size. So you'd have to round this bet of $550 to treat it as if it were a bet of $500 or a bet of $600 in a technique called action translation. And that works okay, but if your opponent knows that you're doing this, they can take advantage of you by intentionally confusing your mapping. Or you also just run into situations where this rounding causes a severe rounding error and the AI becomes confused about the size of the pot, for example. And this was actually one of the key weaknesses of Cloudico. There were situations where it was confused about how much money was actually in the pot because it was doing this rounding and it was creating rounding error. And then it would make fairly nonsensical decisions in some situations. So what safe subgame solving does is it gives us a way to get around this. What we can do is if the opponent chooses one of these off-tree actions, what are called off-tree actions, where that is an action that's not in the action abstraction, we can create a subgame following that action and solve that subgame in real time. And we try to find a solution to that subgame that makes the opponent no better off for having taken that action that is not in the abstraction compared to an action that already is in the abstraction. And if we can do that, if we can make them no better off for having taken that action compared to an action that is already in the abstraction, then we're able to reproduce a Nash equilibrium. And in fact, we have a theorem that says if the off-tree actions, that is the actions that are not included in the action abstraction, are not much better than the on-tree actions, then safe subgame solving will produce an approximate Nash equilibrium in this way. And of course, we can repeat this as we go down the game tree in response to subsequent off-tree actions as well. We conducted a number of medium-scale experiments prior to our competition against humans, and we found that the latest form of safe subgame solving that we use is about 3 times less exploitable than prior safe subgame solving techniques, and way less exploitable than not using any subgame solving at all. And nested subgame solving, the technique where you, instead of rounding off-tree actions to a nearby size, you instead compute a strategy in real time in response to those actions, that has exploitability that is 12 times less than action translation, where you round the action to a nearby size. And in terms of head-to-head performance as well, we find that nested subgame solving leads to far better performance compared to past techniques against other top bots. I mentioned that there is an event called the Annual Computer Poker Competition, where a number of researchers that conduct research on imperfect information games get together and make an AI for a game like Heads Up No Limit Texas Hold'em and play them against each other. The prior champion bot was Baby Tartini in 8. This was the winner of the 2016 competition, and it was actually our entry in that competition. The next closest competitor in that competition was Slumbot, which was beaten by 12 little big blinds per hand. And Baby Tartini in 8 beat Tartini in 7, which was the winner of the previous competition, the 2014 competition, by 25 milli big blinds per hand. There is another AI called DeepStack that came out around the same time as Libratus that also uses nested subgame solving and also has very low exploitability, but in terms of head-to-head performance, was not able to beat Baby Tartini in 8. But our AI Libratus, which uses the latest form of nested subgame solving, was able to beat Baby Tartini in 8 by 63 millibig blinds per hand. In terms of the annual computer poker competition win rates, this is a very wide margin. And this is due almost entirely to nested subgame solving. In fact, if you play Libratus without nested subgame solving against Baby Tartini in 8, it's only about tied in performance. Now, the final component of Libratus is the self-improver. This module reviews the hands that were played in the previous day of the competition, and overnight calculates an improvement to the blueprint strategy that gets it closer to an equilibrium in the parts of the game tree that the AI is constantly finding itself in against the human opponents. Now, if you look at the blueprint strategy, I mentioned that there are a number of actions in the first and second betting rounds, but you don't have all of the actions in there. So there are some gaps. For example, we have a 25% pot bet, a 50% bot bet, 75% bot bet, and a number of bet sizes between that as well. But if the opponent were to bet something like 80% pot, that would not be in the abstraction, and so we would have to round that to, for example, 75% pot, if that action was played in the first 2 rounds. After the second round, so in the third and the fourth betting rounds, we use nested subgame solving to calculate a unique response to that bet size. But in the first and the second betting round, we use this rounding. And for the most part, this is okay because we have so many different bet sizes, so this rounding error is fairly small. But it would always be nice to have that rounding error be even smaller. Now, one option is to simply include more actions in the action abstraction, but that makes it harder to solve the abstraction and compute the blueprint strategy in the first place. So instead what we do is we observe the actions that the opponents were actually taking in the competition. And we find the actions that they are taking that are farthest from an action we already have in our abstraction and that are played most commonly. So we'll score the different gaps in the action abstraction based on how often the opponents are playing in those gaps and how far those gaps are, how far those actions that they're taking are from an action that's already in the abstraction. And then we will compute overnight a subgame, a solution to a subgame that follows that action, and basically glue that into the blueprint strategy. So we augment the blueprint strategy, and now if the opponent chooses that action again, or chooses an action that's nearby to it, we will be able to use the solution that we calculated overnight in response to that action. So in this way, we're able to progressively narrow the gaps that are in the action abstraction, and if the opponents were to find a weakness, it could go away. We could calculate a response to it overnight and basically fix that weakness, and we have to constantly keep the humans on their toes in this way. And the amount of gaps that we're able to fill is basically limited by our computational resources. In Libratus, we were able to fill in 3 holes each night, but if we had more resources, of course, we could use more. Okay, so some observations about Libratus. We spoke to the humans about how it's playing, and in general, they said it's playing like a very strong human player. But it's also doing things that are unusual for humans and are very difficult for humans to imitate. But there are some things that the humans are planning to incorporate into their strategies going forward as well. So one of the things that the bot did that was exceptionally good is that it used many different bet sizes. And this is actually fairly unusual. When top humans play poker, they tend to use 1, maybe 2 different bet sizes depending on the situation. And this is because humans are fairly constrained in how they're able to balance these different bet sizes. If, for example, you're betting more frequently a smaller bet size with weaker hands and a larger bet sizes with stronger hands, then your opponent might be able to pick up on this and be able to exploit you. So to be safe, humans tend to use just 1 or 2 different bet sizes so that they don't run into this problem of incorrectly balancing between these different bet sizes. But the bot is able to do this to a far greater precision than humans are capable of, and so it was able to use 5, sometimes even 10 different bet sizes and balance between them so that there were no tells that were being given away to the human opponents. And this made the bot far harder to predict and allowed it to use a wider range of bet sizes that gave it more of an edge over the humans. Another thing the bot did that was kind of surprising is it did something called donk betting. There are certain situations in poker where it's considered by human players just a bad idea to ever bet. So in particular, if you ended the previous betting round by just calling, it's considered a bad idea to then start the next betting round by betting. This is called donk betting, and it tends to be something that weak players do, not strong players. But the bot was able to find particular situations where donk betting was actually very effective, and it was able to incorporate it in its playstyle. In particular, if a new board card came out that would have given a weaker hand a better hand. So for example, if a low card came out that would have given weaker hands a straight potentially, then the bot, even though it called at the end of the previous round, which signals that it has a weak hand, it was able to then represent that it has a stronger hand by betting in the next betting round. And this is something that the humans found very difficult to emulate, but they also plan to use this and incorporate it into their strategy in the future. Another thing the bot did that I think is becoming very popular among top human players now is overbetting. If you look at top human players, they tend to bet between about half the pot and 1 times pot. And if they're really feeling adventurous, maybe they'll throw in a 1.5 times bet in certain situations. But that tends to be about it. But the bot would frequently bet 3 times the pot, 5 times the pot, 20 times the pot. It had no problem with throwing in $20,000 into a $200 pot. And this put the humans in really difficult situations. You could see them during the competition sometimes taking 5 or 10 minutes to decide what to do when they're faced with one of these big overbets. And it's really frustrating because there will be situations where they have a really, really good hand, but the bot is betting 10 times the pot and is basically saying that it has the best hand. And it's very hard for a human to lay down the second or third best hand when you're faced with that kind of bet, because it's just in general it's a very difficult situation. And the humans said that this is something that hasn't really been explored sufficiently by humans, and it's something that they definitely intend to use in their play going forward. And in fact, now you're seeing in top human play that overbetting is far more common. It's very common. It's a very popular strategy now to throw in a 3 times overbet. Now it's very difficult to do it correctly because you have to balance it with bluffs as well. You can't just always bet a huge amount when you have the winning hand. You have to bluff 3 times or 5 times the pot with as well. And that's very difficult for humans to do correctly. But it's something that the humans are definitely working on and trying to incorporate in their play. Now, as far as weaknesses, I would say the only weakness in Libratus's play is that it wasn't actively trying to exploit its opponents. If, for example, the opponents were to never bluff, the bot would not adjust its strategy to take advantage of that. It would always try to play the equilibrium strategy and try to get as close as possible to the equilibrium strategy. Even in the self-improvement module, that was never looking at the opponent's cards. It was only looking at what actions the opponents were taking and trying to get closer to the equilibrium in those particular situations. So whether or not this is a weakness is kind of debatable. If you want to beat top humans, opponent exploitation is probably the wrong way to go because the humans are so strong that they probably won't have many significant weaknesses anyway. And if you're playing a two-player zero-sum game like Heads Up No Limit Texas Hold'em, if you can approximate the Nash Equilibrium very effectively, very well, then you're going to win an expectation in the long run. You're not going to lose an expectation in the long run anyway. So in terms of opponent exploitation, the only way this is a weakness is that when you're playing against weaker players, you're not going to be taking advantage of them as much as you could potentially. That is, you're still going to beat them in the long run, no question. And you're probably going to beat them by a pretty good margin, but you might not crush them as severely as a top human would that would be able to adjust and take advantage of the weak player's weaknesses. And this is an area of active research, but I would say it's kind of a different line of research compared to the equilibrium finding approach that we're taking. Now, one question I often get is, well, what about 3+ player games? After all, this competition was head-to-head, man versus machine, one-on-one. What if you had three players at the table, 6 players, 9 players, would the same technique still apply? And there's two ways to answer this question. There's the answer in theory and there's the answer in practice. So in theory, if you have more than 3 players at the table, everything becomes far more complicated. For starters, finding a Nash equilibrium is no longer computationally efficient. In fact, even estimating a Nash equilibrium is no longer computationally efficient. But even if you could find the Nash equilibrium efficiently, it's not clear that you'd want to play it. I mentioned that in 2-player zero-sum games, if you're playing the Nash equilibrium, you are guaranteed to not lose an expectation, no matter what your opponent does. But if you have 3 or more players, or if the game is general sum, that's no longer true. You could be playing a Nash equilibrium strategy, and you could still lose an expectation. And there's 2 reasons for this. One is your opponents could just flat out be teaming up against you. If they are colluding against you, there's really nothing you can do. You're going to lose, especially in a game like poker. And even if they're not colluding, even if they're not explicitly colluding, you run into this issue where if all 3 players were to compute a Nash equilibrium independently, then the joint strategy that they play might not be a Nash equilibrium. They could be playing different strategies, 3 different parts of 3 different Nash equilibria. And the combination of those parts is not necessarily a Nash equilibrium in itself. In 2-player zero-sum games, this actually is not an issue. If 2 players independently compute Nash equilibria, they don't have to be the same Nash equilibrium. The joint strategies that they then play against each other is still a Nash equilibrium. But in 3+ player games, that's not true. So even if you could find a Nash equilibrium, it's not clear that you'd actually want to play it in a 3+ player game. And the other issue is that because the interaction between your opponents has such a dramatic effect on can have such a dramatic effect on your performance, it's not really clear how you can't really objectively measure performance in a 3+ player game. This is the reason why, for example, in the Olympics, you don't see any 3-team or 3-player games. You either have 2 teams or 2 players, or you have a game like a race where the players don't interact with each other. There's no way to objectively measure performance if you have 6 players at a table in a game like poker. Now that said, all of these techniques appear to work well in practice, even if there are more than 2 players in poker. And I want to emphasize that this is true for poker in particular. And I think that there are 2 reasons why these techniques still end up working really well for poker specifically. One reason is that even if you have 6 players at the table, most players fold early, especially at top level play. It's actually very rare that you'll get to the 3rd or 4th betting round and there will be more than 2 players in the game. And this is because poker has this fold action, so players drop out very quickly in the game. And in fact, as you add more players, the probability of folding increases in optimal play. So in top play, you'll very frequently have the game come down to 2 players anyway. So you can use a technique that only works in 2-player zero-sum games, and that will work well in practice even if you have 6 players at the table, because there in practice will only be 2 players very quickly. And the other reason is that there really isn't that much interaction between the players. You're not going to run into situations where players try to collaborate with each other and team up against another player. In fact, that's actually explicitly against the rules in poker. It's actually illegal to attempt that. And this is in contrast to a game like Settlers of Catan, where you are explicitly encouraged to try to collaborate with the other players and conduct, for example, trades that are mutually beneficial, or in a game like Diplomacy, where negotiation and teaming up against another player is a critical part of the game. So these issues of player interaction are not really an issue in practice in a game like poker. So for these reasons, the people that I've spoken to a number of people that develop poker AIs, both for research and commercially, and the general consensus seems to be that these techniques have led to superhuman AIs in pretty much all variants of poker. So no variant of poker is safe. It doesn't matter if you're playing six-handed Texas Hold'em or 9-handed Omaha. There are now superhuman AIs in practice for all of these techniques. And I think this highlights that I think 3+ player games are a very interesting challenge problem. I think that dealing with these issues that I mentioned before, the theoretical challenges, that finding a Nash equilibrium is no longer computationally efficient. It's not clear if you want to even play a Nash equilibrium in these games. Dealing with collaboration with other players is a very difficult challenge that we don't know how to address. But for these issues, poker is actually the wrong domain for it. So I want to wrap up a bit now and talk about where we've come and where we're going to go from here. There's this XKCD comic that came out in 2012 that I really like. It lists a bunch of different games that AIs have worked on, and it groups them into different categories. For example, there's this category of solved games like tic-tac-toe, Connect 4, checkers. There's this category of games computers can beat top humans that has Scrabble, chess, and this was right after the Jeopardy competition in 2011. So Jeopardy is right over the line, and computers can beat top humans now. And there's this category, computers still lose to top humans, which in 2012 had StarCraft, poker, Go, and Arima. And there's this category, computers may never outplay humans, that has 7 Minutes in Heaven and Calvin Ball. And in 2017, we've seen that 3 of the games that were in the computers still lose to top humans category have now moved up to computers can beat top humans: poker, Go, and Arima. And it's interesting that Arima was actually specifically designed to be hard for AIs to address. There's one game that's left in this category, StarCraft, which is also an imperfect information game, and which I think that this line of research that has gone into poker is going to be very relevant going forward. I've talked to top StarCraft players that I'm friends with, and they've told me that if you look at top-level StarCraft play, a lot of it isn't the mechanics of the game. A lot of it is the high-level strategy, and a lot of it is strategy that's very similar to poker. There's a lot of bluffing, a lot of attention paid to the hidden information, and what your opponent knows and what your opponent might think about about what the game situation is. And I think that this emphasis on hidden information is being neglected by the research community that is working in real-time strategy games like StarCraft, like Dota, and like League of Legends. I think that if you want to reach a superhuman level in these games, understanding and addressing the hidden information component is going to be very relevant. But I think that this comic also illustrates that we've made a ton of progress in AI, and it's not really clear what the next steps are. So for me personally, I think that some future directions that I'm very interested in, one is a grand unified, what I call a grand unified theory for game AI. We have AIs now that can play superhuman level in Go, chess, and poker. But there's a disconnect now between AIs that can play superhuman in perfect information games like Go and chess, and AIs that can play at superhuman level in imperfect information games like poker. And I think it would be really nice, it would be really valuable to have a single algorithm, a single AI that can play all of these games at a superhuman level. And that's obviously something that I think a lot of people are interested in, but I think it's going to be very challenging, and I think that there are going to be a lot of steps needed to bridge that gap. Another area of future research that I'm very interested in is what I call semi-cooperative games, or general sum games. These are games like Settlers of Catan, Risk, Diplomacy. These are games that have potentially more than 2 players. It could be 2-player general sum, but these are games where it's not just about taking money from your opponent or beating your opponent. It's about teaming up with players, at least temporarily, to try to reach some common objective. And so these games involve a lot of negotiation, a lot of trading, and a lot of understanding how the other players are going to interact with each other. And this is something that AI, at least AI currently, isn't able to address in a principled way. This is an area of research that is very new, that a lot of people are struggling with, and it's not even really clear how to measure performance in these games. So I think that this is going to be a very interesting and very active line of research in the coming years. And finally, there are real-world applications, and I think this is important. AI has, in the past few years, focused very heavily on AIs for games, and I think there's very good reasons for that. But I think that also the technology has evolved to the point where we can start looking at real-world applications and what the real-world potential is for these different algorithms. And in particular, I think that the AI research that has gone into poker has short-term applications to areas like finance and negotiations and security interactions and auctions. Obviously, the big challenge with these sorts of real-world applications is converting a real-world interaction into a model that has well-defined actions and well-defined payoffs. But if you're able to do that, then you can apply these techniques and I think reach very interesting strategies, and it will be very beneficial to the world as a whole and contribute a lot to the social welfare of society. So I'm going to stop there. If you're interested in this research further, I encourage you to visit my website. I have a number of papers related to this research that are listed there that I've published. And I also want to take this opportunity to point out that even though Libratus was the first AI to beat top humans in this game, the reason we were able to do this is because we were building on about 2 decades of research from a very active and very open research community. For example, a lot of the abstraction techniques that were really critical to forming the blueprint strategy came out of prior research from students at Carnegie Mellon, for example, Andrew Gilpin and Sam Gansfried, and research conducted at the University of Alberta. Monte Carlo CFR and its predecessor CFR came out of University of Alberta, researchers like Mark Langtodd and Martin Zinkovich. And CFR Plus, which was a variant that's been very successful and was critical in the subgame solving, came out of independent research from a researcher in Finland. Subgame solving was originally developed by Neil Birch and was built upon by independent researchers like Eric Jackson and researchers at Charles University in Prague. So I think this really goes to show that the poker AI community has made a ton of progress very quickly in the past 12 or 15 years. And I think the reason for this is that partly we had this competition that encouraged a very friendly but fierce competition between different research labs. And also we had a very open research environment where after each competition people would share the techniques that they've used in the latest developments and would publish that research and would be very active in answering questions and helping other people that wanted to be involved. And I think that that is the kind of approach that's really needed going forward, not just in the poker AI research, but also in other areas as well. It's very important to have an open research environment and to build upon other people's work. So I just want to thank the research community in general for giving us those resources and doing that prior work that was really so helpful in achieving this. So I'll stop there. Thanks.